Hello, everybody. We are after our first Skype meeting break, and I'm very happy to introduce the next competing Samba school in today's competition. And the name is Gonçalves. And if you are wondering what the title is, the title is Nonwandering Sets and the Entropy of Homeomorphisms. It's all yours. Take it over.
Thank you, Kurt. So thank you all for attending this talk. Thank you, Gilles, for inviting me, Kurt. This will be something new, talking, writing on the computer and to an audience at the same time. We have not done this here. At least I have not done this even during the pandemic. We usually just did like the online classes at home. I know that in the US, people kind of did this kind of thing, but we didn't go through this experience, so this will be new. I also was planning a Blackboard talk, but then I arrived here and Gilles surprised me with all this technology. So let's see. So the setting that we have today, okay, our setting will be local homeomorphisms, which I think most of you know very well. But anyways, we start with, say, a local homomorphism, right? We have X, a compact space or locally compact. So X, a locally compact space, locally compact. And you have an open subset of X, which will be the domain of the map. A domain here, a domain of a map, which we call sigma. And you have this map, which is the local homomorphism from the domain back into X. Right? So sigma is a map from the domain of sigma. This is an open subset, this is open, into the image of sigma, which is also an open set, which is also open. And this is a local homomorphism, which means that every point here has a neighborhood where the map is a homomorphism. Every point in the space has a point where it's a homomorphism. Okay. So this the pairs X with sigma are also known as diagonal-Renault systems, right? Diagonal-Renault systems. Diagonal-Renault systems. And I think they were originally called singly generated dynamical systems by them. And they are like the basis, the building blocks of many string system algebras, right? As graph system algebras, subshift algebras, and many more. So just to make yourself clear here, a little bit of notation. Since we have this domain, right? We have the space and we have the domain where we cannot apply the map at every point. When I say, when I have a subset of X and I say sigma of Y, I'm actually saying, right, sigma of Y intersection of the domain of sigma, right? This is implicit, right? I'm intersecting with the domain. So as I said, right, some examples, these include like graph algebras. Let's say if you have a graph here, it can be like, oops. Yeah, this is okay. We can do different one. But it could be, you can take X to be the boundary path space. The boundary path space. Boundary path space. So, which is all the infinite sequences. All the infinite sequences. Union with the finite sequences ending in infinite emitters. And let's say we don't have sinks. So finite sequences ending in an infinite emitter. So that's your space. The map is just a shift map. And topology is the usual topology for cylinders, except for if you have an infinite emitter here. Say if you have an infinite emitter, sorry about this. Then for this finite sequence arriving at this infinite emitter topology, you're going to specify the cylinder here, and you're going to choose a finite number of edges departing this say that edge E there that you're gonna avoid. So you will choose a fine number of them that you avoid, and you say a neighborhood here is all the paths that start with that specified beginning and avoid this to continue this finite number of edges that you specified.
How do you do shift?
Just doing one side shift. So
you jump from one branch to another.
Let's say if I shift just something like this, you just go to the empty word, right? You have an empty. You go to this vertex here. You have a vertex which is a path of length 0. So if I have a shift of just the left, this is a finite sequence. This would be just V, the vertex V.
And here stop.
And here stop. Yeah, the domain, right? The domain of the map is just all the paths of length greater or equal than 1. You have to have length greater or equal than 1. And then
infinite sequences can also ask to do with the emitters or no?
They can. They can. Yeah, infinite sequence can go to infinite emitter here and continue and go on. Yes. Right. Yeah, so we have all these infinite sequences in the graph, right, that you can get. And when you get an infinite emitter, yeah, you stop there, you got a finite sequence that you add in your space. And the neighborhood of this finite sequence might be different. And okay, you start to erase the entries, and eventually you get to something of length 0, right? If you're like in something like the ON, like here, right? Like I was doing there, like this, then you just have one vertex, right? But if you have more infinite emitters, you might have more. Okay. So this is go page down. Okay. So other examples for ultragraphs are also ultragraphs. Nice example that you get. So ultragraph is like a graph, but the range of an edge might have more than one vertex. So the range of an edge might like do a bifurcation like this, for example, and the range might have is a set of vertices. So you could have, I don't know, say 3 vertices for an edge. So this would be just an edge, and the range here could be a set. And then from here, I could have maybe infinite number of edges coming out of here. All right, I could have just a fine number one here coming out. I could have, and then this is joint work with Danilo Hoyer. You can see here this space of all infinite sequences, right? The boundary path space here. A nice one to look. Sorry?
May I interrupt you, Daniel? I see your face, but I don't see the page where you are supposed to be writing. You're supposed to be writing on the screen, right?
Yeah, I am writing on the screen, but they're not seeing.
Yeah, but you are showing your, I see a window with your face in it,
okay.
But I mean, and you gesturing, but I'm not seeing the screen. You should share your.
Guillermo, I think it's a problem with you because I'm seeing the whiteboard of Daniel.
So
I used to be. I saw it until a certain point when I didn't see it anymore.
But there must be a problem at your end.
But how could that be?
I mean, we see it.
Yes.
It's hard to help you fixing it because it's a problem of your Zoom, not our transmission.
I think maybe he has to shift what he's seeing. This is the.
Yeah, but I mean, is there another window that with another name? The window I am seeing Daniel in is Gilles Gonçalves de Castro.
That's fine. Yeah, because he's using his laptop.
Yeah.
And he's going to connect. Yeah. But you should also see, like everybody else, the shared screen. I mean, I'm using a different Zoom account.
Okay, so I'll leave and come back and see.
Yeah, exactly. That's the best option, yeah. Connect again, yeah. Okay, so let's go on.
All right. So ultragraphs, I don't want to spend too much time here, but just say that they are good models for XO-like algebras, for the algebras of infinite matrices. So here you get all the infinite paths, and you get finite sequences that end in a minimal infinite emitter. It's not all ultragraphs that you get this way, but a good portion of them. So for example, a minimal infinite emitter here, like I just draw this one here, an edge here, the range of this edge is these two vertices, and you have two infinite emitters. So it's not minimal because the range contains two infinite emitters. You like to have just say one of them. It's not exactly this, but it has to be minimal in a certain sense. So this is something that I did with Danilo. So these are, maybe I can put here GR if someone is interested. It's a interesting notion that we have to build the C-star algebras of these ultragraphs and to study these boundary path spaces. Other examples, simple examples that we can look at. Let's say you have the Cantor set, the usual. Yeah, here, for example, you have two vertices. Yeah, you have two finite sequences. You have EV1, you have EV2. Yeah, the finite sequence here, I'm lying a little bit here, and the minimal infinite meters, they come with pairs. You come the finite sequence, comma, a subset of vertices, which is a minimal infinite meter. It's not just the path, you can, so you need this vertex where it arrives. So here you'd get, for example, two elements from this side.
So do you attach the next path to all vertices or just to some? When you concatenate?
Sorry?
When you concatenate, how
Yes.
do you concatenate?
Oh, you concatenate, if you can concatenate if the source of an edge is contained in the range of the previous one. It's contained. Belongs, yeah, belongs, yeah. Belongs.
In that case, for example, the shift gives you which one of the two vertices. If you are more than one, right?
Right, no, but I mean, okay, so what are you saying? Which path do I have? You want to shift to which, what you want to shift?
One edge about the meter with more than
Okay, so you have just infinite paths. So, okay, infinite path is the usual thing, like say here, E, F, so on. So the E, F, or F2 and so on. So you just shift, usually just erase the first one. But if I have something like here, E1, say I have a path E, E1, E, and then I have this kind of funny thing, right?
Yeah.
I have followed by this. So when I shift, I kind of erase this one, and I'm left with this pair, EV1.
okay. There must be only one vertex. The final path.
Yes, in the final path you just have one. You cannot have both. That's the thing. You cannot have something that has two. So that it's well defined. Okay, so the Cantor's. Okay, so this is a simple example here. The Cantor set. See the Cantor set. You can say the domain. Just multiply by 3 here and take the domain of the map to be, let's say, your left interval, 0, 1/3 intersection of the Cantor set, and your map to be, oops. Oh, what happened here? Oh, let me see. I'm pressing something. I think something happened to this. Let's see, something happened. This, I think, this got stuck or something. Let me see. Yeah. Do you know what will happen here?
Press again. Maybe there is something on the path.
Let me see. Yeah, it's maybe the paper. No idea. Let's see if you can check this. I'm not. Is it good? Okay. Okay, sigma. Thank you. sigma x equal to 3x. Okay, and so this is an example of a local homomorphism, right? You just have the map from this smaller interval. It's expansion, right? It's just of course, you can get this as Gilles was showing before, and something similar into the Sapirnsky triangle if you want, right? You can do the Sapirnsky triangle and just get something very similar. Get the smaller triangle here into the bigger one, and give you also a local homomorphism. Another nice example that we used to work here is the autotone for Willis subshifts.
So in the table of fractals, can you take the inverse in some sense of any contracting map or that is for shown? If you have more contracting maps, right?
Mm-hmm.
If that is the one, some kind of inverse of one.
In general, just get a small. I think so. I think you can get a smaller one and just inflate into the bigger one. I mean, I have to check, but OTW full subshift, full shift, full shift, full shift. So OTW here stands for autotone for the Willis. So these are shifts that have been introduced recently recently, now it's been 10 years, for infinite alphabets. So it starts with let's say, a countable alphabet. Well, it doesn't need to be countable, but let's take a countable. And your space is all the infinite sequences. So A to the N, union to with the union from N equals 0 to infinity of A to the N, all the finite sequences. And so that's your space. And so just again, it's one side, you have the sigma to be the shift map. And you have an empty word, which is usually noted by this. Empty word. This is connected to C-star algebras, to shifts, subshift algebras. We have a lot of recent work with Gilles, Boava, and Danny. They originally connected with graph C-star algebra, this shift, where they applied this for graph algebras and show that their shifts are conjugate if the algebras are isomorphic. And what else do you want to say here? The domain here, the map, the domain of the shift is all the sequences of length greater than 1. So are the x in x that have length greater or equal than 1. And the cylinders are very similar to what we did in the boundary path space. The usual cylinder sets for the infinite sequences. And for the finite sequences is, again, that thing is the kind of a generalized cylinder set. So if I have a finite sequence, say if I have x1, x2,
There's a
xn.
question on chat. Is unique the empty word?
Yes.
Yeah.
Unique. And we have z of xf. And here we're going to say f contained in A finite. So this is equal to all the elements y in x, such that y 1 to yn is equal to x1 to xn, and yn plus 1 does not belong to f. Yeah, okay. So again, I'm avoiding, I have a cylinder set condition here. So I'm looking at all the elements in this shift that agree with x in the first n entries, and the next entry avoids these finite ladders that I chose. Okay, so that's the key to part of the topology. So this gives us the Achnor-Renault system. All right. Okay, so well, that took much more longer than I thought. Since I was going to talk about non-wandering sets and all that, I have to worry about restrictions of the Achnor-Renault systems. when, right, so I have a local homomorphism, a diagonal system here. I have a domain, and I want to restrict to some y. So I have a y here. Right. So when can I talk about a restricted diagonal system? Right. So of course, when I look at y intersection with the domain, right, so if I look at y intersection with the domain of sigma, right? So I start with I start with x sigma a diagonal system. Y intersection with the domain is an open set in y. But then I want, right, that when I apply sigma here, I want to get an open set of y. So I have to ask that sigma of y intersection of the domain of sigma is open. I want to ask that this is open in y. This has to be open in y, right? Okay, so when this happens, so if this happens, if the image of y intersection of the domain is open in y, then we get a restricted system. And then we denote by y sigma, y is the restricted system. All right. Now, one thing that we prove is that if you have x sigma, a diagonal system, if I get a subset that is invariant by sigma and its inverse, so it's sigma minus 1 invariant, then you get the y sigma restricted y is also the diagonal system. Sorry?
Why is the universe is of the type of that, right?
Right.
So,
Right. We want sigma minus 1 of y to be contained in y. At the preimage. Yeah. Okay, I didn't define, but sigma is the direct application. Sigma inverse is the preimage. Yes. Okay. Yeah, I didn't say that. Sorry. So no wandering sets. Let's see if I'm gonna get to the end of this talk. Definitely not. No wandering sets. So in the classical setting, in dynamics, you have a compact space and a homomorphism. X compact and phi a homomorphism. Right? So we say that point X in X is wandering. Right. Now, if it has a neighborhood that wanders, right? If there exists U open neighborhood of X such that X belongs to U, and right here, phi n of U intersection U is equal to empty for and greater or equal to 1. So you have an X here, and then you have an open set around here, around X, a neighborhood. And when you apply your phi, right, it just goes around their space. You can go back there, but it doesn't. When you iterate this phi of U here, right, it doesn't go back to your neighborhood. You can find a little neighborhood where when you apply, it never comes back to you. Okay. And there's no wandering.
I think n for n sufficiently large, not for n bigger than 1, because x is itself in U, I think. Do you mean for n sufficiently large, or you mean for n bigger than 1 in the definition of wandering?
Okay, I think the one we got is n greater or equal than 1, but I wonder if they're equivalent. You mean that it should be n for n sufficiently large? Why?
Yes, I mean that. Do you mean for n bigger or equal to 1, or for n
Yes.
sufficiently large? Maybe they are equivalence definition for wandering point.
Yeah, I wonder if maybe they're equivalent, but the one I'm using is n greater or equal than 1.
Mhm.
That's where we have. I wonder if they're equivalent. Oh,
Yes,
no
yes.
wandering. If it's not wandering, right? So
Yeah.
oh, the ring. Okay. Right. So this means what? For all open set, for all neighborhood U of x, right? You can find an n such that Pn of u inter u is different than 2. Okay. All right.
Well, in a way, it's still wondering, but it's coming back.
Yeah. Yes.
It'll probably go far.
Right. And these sets are invariant, right? So they're both invariant. They're both invariant sets. Invariant sets. Right? You can clearly see, right? If I get a point here, no wandering u here, if I apply the math here and get a phi of x, I can just get the neighborhood, the phi of u here. That's going to be a neighborhood that's going to wander. Right? That's going to do you the wandering. If you suppose there is a, right, I did too small the picture here, but I think it's not hard to check that this, for example, the wandering set is invariant by phi. If I get a point, get a neighborhood u. If I apply phi of x, apply phi to x, I get phi of x. I look at phi of u, that neighborhood there, there's never going to come back to it, because if it does come back to it, I can just apply the inverse, since I'm in the homeomorphism case, and then I'll get the contradiction to the fact that x is, because I'm in the homomorphism setting.
Wandering set is the set of all wandering points.
Yes.
Or every set,
Yes, the set of all wandering points. Sorry, I didn't define. Sorry. Yes. Wandering points is the set of all wandering. Yes. 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 So we can actually say the set of all wandering points. Wandering points and the set of all non-wandering points. Wandering points. Okay. Now, if we're in the local homomorphism case, we have to really be careful how we define now. How are we going to define a wandering and a non-wandering point? So let me give you a very simple example. So like I get x to be just a discrete shift space. So 2 points, 0, 1, infinity, and 1, infinity. A discrete space, discrete space with 2 points, and the shift map. With these 2 points, and shift map. And the shift map. So here, but basically, right, the shift of 0, 1, infinity goes to 1, infinity, and 1, infinity is a fixed point. So you can see that 0, 1, infinity is wandering. Wandering, right? Because you shift it once and it goes to 1, infinity, never going to return to itself. So clear, and 1, infinity is not wandering. It's a fixed point, so it's not wandering, not going anywhere. So clearly, right? So we get that this set here of wandering points is not invariant. Is not invariant. Right, so this is a problem for us. So this, yeah, we have to be careful how to define this. So the approach that we did with Tasca and Royer and myself was the following. So we say that if you have, we have to look at pre-images. Okay, so if you have X sigma local homomorphism, or the Acron-Renault system, how I like to call more, the DR system. We say that X in X is wandering. If you can find an open set, there's this U open, such that, so the condition is, okay, so we had to look at the interactions, for the interactions of this set U, and before we wanted to not come back to U itself, right? But now I also want to look at the pre-images of this future. So I want to look at sigma minus K or sigma K of U. This is empty for all n greater or equal to mu, and for all K in Z. This, yeah, okay. So this is the key definition. And so if I don't know if I can write here, but if I have a U here, U, and then I want to apply sigma of U, and then I want to look at the pre-image of it, right? So when I look at sigma inverse of sigma of U, of course it has U, but now since I'm in the local homomorphism setting, when I'm in the inverse image, there's also some other guys here. When I look at the inverse image of this one, right, it appears some other guys, right? Okay, and I want these pre-images of these guys to not intersect that one. Okay, so that's the idea. Okay, and of course we're gonna say that this set is no wandering if it's no wandering. Okay. And you can see that right in the classical setting, if you have a homeomorphism, right, then the sigma minus K, sigma K just goes away, and you are back to the classical definition. You just get exactly the usual definition. So
the example you had before, now which parts are wandering and not wandering with this definition. To one discrete example.
right, one of them, let's see, what's fixed is still no wonder. I think everything is no wandering now, I believe, because it's a good question, but I believe everything is no wandering in this example now. This guy here becomes no wandering, no?
Both wandering and no wandering sets are invariant, right? So
Yes, they're gonna be invariant now. Let's see, the 0, 1, infinity.
but you cannot decompose as two invariant subsets.
Disjoint. You mean?
No.
No, these are gonna get. They are both gonna be in this definition here. You mean? They go. I think 0, 1, infinity now. When I let me see.
So this is a stronger definition of
Is-
wandering.
Is strong, yeah, because 0, 1, infinity now is gonna be no wandering here. It's gonna be.
So they're both no wandering.
They're both no wandering. Yes. So you're not gonna decompose. Yes, in this case, they're both no wandering. Yes. Yeah, it's not as useful. I mean, it's a price you have to pay.
Sorry, I'm a bit confused. How does this part depend on K? So I take what? I get sigma K, I apply it, K runs to the integers, and when I take the understand pre-image under sigma k. And somehow does it really change when I run my k? I'm having problems imagining how this depends on k.
But that is the k equal to 0 and k equal to 1, that
Yes.
because the k equal to 0 is just
Identity.
Yes.
Okay, but say you go beyond 1 and 1.
we have more pre-units. That is not that. They go back to 1 and back.
Yes, exactly.
Okay.
Because all the possibilities that of getting a pre-image, and then eventually you could then intersect there in some future, and then you could pull back all this intersection to your original thing. It's all, we're kind of taking away all the possibilities of going wrong. That's the idea here.
Okay. I guess I just would like to see it completed.
Okay. Okay, so these sets are invariant now. These are proof. W and omega are invariant. Invariant. And okay, so some examples maybe. Okay, not very nice examples here, but okay, maybe if I skip all the way to the end, but for the shifts, we kind of characterize for Willis shifts, we characterize them by the left. I'm not gonna get there. Some examples. Every fixed point is non-wandering. If you had that expansion that we had before, say in the Cantor set, right, that we had multiplication by 3, sigma of x was 3x. Then for this expansion, we just have here 0 is non-wandering because it's a fixed point. Non-wandering.
Who came up with this terminology? Non-wandering.
This is a classical terminology of dynamical systems. There's these classical results that say the entropy is concentrates on the non-wandering set. So
don't like this terminology to be non-recurring.
yes, that's okay. That was not us.
Yeah, I'm not blaming
You are one that you cannot, but
Yeah.
always back to the same place.
Yes, exactly.
Yeah,
And
okay.
I'm wondering who came up with this term. Who drink a lot of Californians and they go back home. Yes.
Okay.
Oh, we had to talk about the drunkard 6 hours. We had a talk. Yes, drunkard 6 hours.
And maybe skip away a bunch of pages and maybe some people will be interested in this, but I don't know, for those who knows, in this context of Otton from Willis shifts for OTW subshifts, but this is some work, so we have that, for example, eventually periodic points are non-wandering. If you have a point that contains a neighborhood, right? If a point, sorry, such that every neighborhood contains an eventually periodic point, then it's non-wandering. And we have, for example, that every infinite sequence that is not eventually periodic and is isolated is wandering. Okay. And well, and then the finite elements, there are they are either all wandering or all non-wandering. So we have examples of cases when they are the finite elements, and you can just, since the sets are invariant, it's enough to determine what the empty word does. So finite elements that are all wandering or all non-wandering. No wandering. Okay. So these are some examples. 40. Okay, so the idea that we wanted to do, okay, just before I go to the entropy, to say a little bit about entropy, I just want to make a quick proposition, is that the set of non-wandering is closed, and is contained in the closure of the domain. Okay. So because we're going to restrict the entropy to these sets, right? So the main theorem is that if you have a diagonal system and the domain is Klopen, and then you can show that the entropy coincides with the entropy here in the non-wandering set. So this for the metric entropy. So just to give an idea of what the entropy is. So entropy writes an invariant systems that measure a little bit the complexity of the system, also the exponential growth of how the iterates of the points get apart. So since we're dealing with not necessarily compact, right? Most of the theory is done for compact space, but Bowen has a notion of entropy for non-compact space. And there is a notion of entropy for metric spaces, and for non-metric spaces, I'm going to use the metric one, because our spaces, everything that I showed here today, example is metric. There's a metric. Even the atom from Willis subshifts, the ultragraphs, all that have metrics. And so this entropy here is based on looking at nets of compact spaces, nets and separated sets. So you're going to measure distances and distance between the iterates. Now the problem is if you have a diagonal system, you cannot necessarily iterate a point forever, right? So you have to deal with that. So this is another work that I did with Danilo and Felipe, that we generalize this notion of Bowen to diagonal systems. So we start with X sigma, diagonal system, and we define for every X in X, we define an N here, N natural. We define an IN of X to be, oh, this doesn't, the I in 0, 1, N minus 1, such that X belongs to the domain of sigma I. These are just all the numbers that, the powers which I can apply sigma to X. Of course, if you can apply N minus 1, this could be just a number, right? It didn't need to be an initial segment of the naturals. It's just, for partial actions, this was important. We did some previous work on partial actions, and so we just kept the notation. So then we have to define a metric. Sorry, we have to define a map here, which is dn of xy. I want to measure the distance after the maximum distance between 2 points between their iterates, right? Iterates the map. So this is the maximum of the distance of sigma I of x, sigma I of y, where I can iterate, right? I is in the intersection of I n of x with I n of y. Okay, so this One of the big problems we face when we do this theory is that this is not necessarily a metric. This,
So you assume that geometric space is given, right?
yes. Yes, I'm assuming that this is metric, actually metric. Metric, yes. But this dn is, d is a metric, but dn is not a metric. Not necessarily. This is, you have examples where this, the triangle inequality fails. And then
The end is defined on omega.
dn?
It's only defined on non-wandering.
No, this is defined, no, this is general. For any diagonal system now, a n could be, well, I'm
Why not?
zero, yes. Zero. And then you have the metric itself. Okay. So, so the definition of the Bowen definition of entropy is the following. So we got a compact set. Compact set containing X. Everything works so well for compacts. And in the naturals, and let's say Y a subset of X. And let's give an epsilon greater than 0.
Sorry, but you cannot never get it infinite, right? Because in principle, there are parts that you can apply.
Right, but this dn, I'm just applying up to n.
Okay.
The distance. I'm applying the iterates of n up to n times. Then later there'll be some infinites, but so we say that a subset A. So A is just Y is just any subset of X. We say that A containing K inter Y is an n epsilon. Well, let's put everything n epsilon sigma K inter Y separated set. Separated set. Well, if dn of xy is greater than epsilon for every xy in A. Okay, of course, x different than y, right? So you have your x. We have a domain here. And then we have what? We had a compact set in X. And we had K inter Y. Well, let's just do a set here. K here. And so we have this set of points, this A. And any 2 points here, the distance, not necessarily, maybe they're very close. But once I apply the map, the iterates, they get farther than epsilon, right? So this set here is n epsilon separated if their distance is greater than epsilon. So write a remark is that sigma n of x may not belong to K inter Y, right? It might get out of this set that I have here, K inter Y. And okay, so this set that I have here, this point is separated. There's also a notion of spanning set, or which is well, let's say B containing K inter Y. It's just a net. Is a spanning set. Spanning set if for all Z in K inter Y, there exists a B. Exists B in B such that the dn of BZ is less than epsilon. Okay. Now you take what we're interested here is we let SEP of an epsilon to be the maximum cardinality n epsilon K inter Y to be the maximum cardinality. Cardinality of a separated set. Separated set, right? So you look at all the possible separated sets in K inter Y, say, here, and look at the maximum cardinality, okay? Now, that's why you need this compactness here, because, look, if you have a set here that's set of maximum cardinality, right? A separated set of maximum cardinality, if you put one more element, is definitely, this is already a spanning set, right? Any extra element there is a distance less than epsilon from the other ones, because that one had maximum cardinality. And these guys here, covering by balls, we can show that's finite, so you can actually show that these guys here are finite. Then you can actually get a finite bound for this. Okay, so this is the key idea of the entropy, right? Is looking at how these sets grow, this maximum cardinality of these separated sets. Now, okay, right. But for us, how we're gonna define for us our things is the following way. Definition. Okay, because we remember we are in the setting of the local homomorphism, right? So we have the space X, and we have this domain. We don't have necessarily a compact space, right? So we have this domain here. I can get a compact space set subset here, but it's not necessarily my whole space. No, I don't. There's this K here. So what I'm gonna do? This domain here now intersection with this compact, I lose compactness altogether. So the idea is to get this compact and this domain here is to approximate this domain by Klopen sets from inside. So I start to look at Klopen sets from inside and intersect with this compact there. So I get a closed set inside there. And I do the intersection of this compact, and then I get larger and larger closed sets, and they'll do the separated sets that I had before. So if I have K containing X compact, and greater than 0, epsilon greater than 0. So we define the SS set. This is something that we introduced, and epsilon sigma K. This is the supremum over all F of n epsilon sigma K inter F, where the supremum, right, is taking F is a closed set contained in the domain of sigma n minus 1. Okay. All right. So now we have a way of approximating this classical notion of set, of this maximum cardinality of separated set. And now we can define the entropy. So then we have to take H epsilon to be, we have to take lim sups now to see how this thing grows with n. So lim sup as n goes to infinity of 1 over n, of the log, because you want to see the exponential growth of that. So of SS sep of n epsilon sigma K. Okay, then the next step there is to take the limit when epsilon goes to 0. Limit when epsilon goes to 0 of H epsilon sigma X. I did not write everything here, right? H epsilon sigma KD, sigma KD. And at the final step, you take the entropy of the system to be the sup over all compacts of HT. Yeah, it's a lot of sups. It's not simple, but the key part is this set part. So that's the definition for our local homomorphism. And these 3 steps here, okay, this is classical, but this definition here, or the step of approaching the domain by Klopen sets from inside, this is, I think, when we have, our contribution there. And then in this more recent paper, our theorem, there's two theorems. One is that the entropy of a system is always equal to the maximum of the entropy restricted to the non-wandering set, and then the entropy restricted to the closure of the wandering set. And the other theorem is that if you have X compact and the domain of sigma Klopen, then the entropy of sigma is actually equal to the entropy of sigma restricted to the non-wandering set. Okay, so they're the main theorems that we proved more recently. And then we applied some examples where we can apply this, where we can compute the non-wandering set and show that some entropys are 0, some entropys log 2. And we characterize the non-wandering sets for these auto-from Willis subshifts. We have also computed entropy for row finite graphs in our first paper. So for row finite graphs, if they're locally finite, that's very nice. But they're usually the supremum of the entropies of finite graphs. And actually then use the usual entropy theory for finite graphs. Okay, so that's for that Cantor set that we had an example that ends up being 0. It's interesting, right? Because you had this and then this, but then you just have one fixed point. And the domain is Klopen, so we can use the theorem. The X is compact here. Domain was just this part, but the non-wandering set was just this fixed point here. The thing of this, I know the maps is an expansion, but the domains are shrinking, and that makes so that it doesn't grow so much, the distance between the iterates. So the entropy actually gets to be 0. Yeah, but it gets really easy to compute with all those formulas, but when you get to apply the theorem, and then just get the 1 point, and then you guys, okay.
I thought somehow entropy and Hausdorff dimension were related, but I'm not sure about it.
I think if you
has a positive Hausdorff dimension.
Yeah, if you get something like say in R, like just 2x or 3x, you're gonna get log 2. You get a map from R to R, just 2x or log 2, 3x, log 3. But here, since you're making the domain shrink, then that makes it not good. All right, so that's.
First from the room. Go ahead.
Does this wandering set and non-wandering sets are related because for CQS or to the 250 points? But you talk about almost periodic points, so it's good. There's
Right, so there's other people, the eventually periodic. It could be, but I'm not sure. I mean, we have some examples there, some weird behavior for things, but it'd be interesting to look. I'm not sure.
Francesco. Anybody from the Zoom?
maybe I'm just, it's not a mathematical question, but so if you let this, for example, the entropy that tell you something about the parameters of this system.
So there's this whole theory of system algebra of yes, and I've always I don't know enough about them to relate, but I'm pretty sure they must be related. And maybe I have to study that to say, because the entropy, right? Because you compute for these diagonal systems, which are the building block of the system algebra, so they must be connected. I just have to study more to be able to answer that. It's a very good question, I think.
And it's a mathematical.
Yes.
Okay, there are no more questions. Let us thank our speaker again. Thank you. And our next speaker is Professor Almoso. And he will speak in Labohem. So
Excuse me, for a moment, I lose the conversation.